Hello everyone, myself Prashant from BSC Chemistry Honours first year. Today we are gonna read chapter alkanes and cycloalkanes. So first part is alkanes and here is the introduction starts. The simplest organic compounds are hydrocarbons compounds containing only carbon and hydrogen. The hydrocarbons may be saturated or unsaturated. They may have either open chain or ring chain structure. Due to these variations, they are divided into various classes. One of them is alkanes. Alkanes are the simplest open chain saturated hydrocarbons having the general formula CnH2n plus 2. The bonds in alkanes are formed by the overlapping of sp3 hybridized orbitals of each carbon with similar orbitals of other two carbons or 1s orbitals of hydrogen atoms. As such, alkanes contain only sigma bonds. As these sigma bonds are quite strong, they are not easily attacked by reagents. They do not react with the usual laboratory reagents under ordinary conditions because of their low chemical reactivity. They are termed as paraffins. Latin param means little, affin means affinity. Structure: each carbon atom is sp3 hybridized with its four hybrid orbitals directed towards the four corners of a regular tetrahedron. The following structure shows a molecular model of the simplest alkane, methane, also shown in a 3D representation of the molecule where the wedge represents the bond pointing towards the observer out of the plane of paper, the hatched line representing the bond pointing away from the observer behind the plane of paper, and two normal lines represent the two bonds in the plane of paper. Each carbon-hydrogen bond length is 110 picometer and each hydrogen-carbon-hydrogen bond angle is 109 degree 28 minutes. Here are three structures. A overlap of 1s orbitals of 4 hydrogens and sp3 orbitals of carbon. B. Simple three-dimensional representation. C. Bond lengths of and bond angles. Formation and structure of methane. Similar in is the case of ethane. Each carbon atom is sp3 hybridized. The carbon-carbon bond is formed by the overlap of sp3 orbitals of each of the two carbon atoms. The remaining hybrid orbitals of both the carbon atoms overlap with one s of hydrogen atoms. A. Molecular model and B. Bond length of the bond angles and bond angles. Molecule of ethane. On the account of tetrahedral arrangement of the four bonds formed by each carbon atom and the alkane molecules are three-dimensional in nature. In case of alkanes containing more than two carbon atoms, it is observed that all the carbon atoms of the chain do not lie along a straight line, but carbon-carbon chains may assume a variety of zigzag chains as shown below in for propane. Molecular model of propane showing that the carbon atoms do not lie along a straight chain, but for the planar representation they are written in a straight line. Type of carbon atoms in alkanes. Alkanes contain four types of carbon atoms. Primary carbon atom which is directly bonded to either one or no carbon atom. Secondary carbon atom which is directly bonded to two carbon atoms. Tertiary carbon atom which is directly bonded to three carbon atoms. Quaternary carbon atom which is directly bonded to four carbon atoms. For example, the following formula has 5 1 degree, 2 2 degree, 1 3 degree and 4 4 degree. Now 1 4 degree carbon atoms. Here we can see this one is primary, this is one is tertiary, primary, secondary, primary, quaternary, primary and primary. The hydrogens may also be qualified as primary, secondary, tertiary according to as they are linked to primary, secondary, tertiary carbon atom respectively. Thus in example below there are 15 primary hydrogen atoms, 4 secondary hydrogen and 3 one tertiary hydrogen atom. Nomenclature of alkanes. There are three systems of nomenclature. First is the common or trivial system of nomenclature. In this system, the first four members have special names: methane, ethane, propane and butane. The higher members are named by prefixing the Greek numerical indicating the number of carbon atoms in the molecule to the suffix "ane". Thus, the common names of the alkanes are as listed on the table. Common names of This is the list: methane, ethane, propane, butane, pentane, hexane, heptane, octane. The isomeric alkanes C4H10 onwards are named as follows. If all the carbon atoms are present in a straight or continuous chain, they are termed as normal or anhydrocarbons. Second is IUPAC. Third is IUPAC system. It is based upon the following rules. The longest continuous chain of carbon atoms, called the parent chain, is selected in the molecule, and the compound is named as alkyl derivative of the parent alkane containing this chain. The branching is then numbered from the end, which gives the lowest set of locant for the branching alkyl groups, which means the numbering of the parent chain is done in such a manner that the alkyl substituents gets the lowest possible number. The names of the branching alkyl groups are then prefixed along with their position numbers before the word root is alphabetical order. For example, 2-methylpentane, 3-ethyl, 3-methylhexane, 3-ethyl, 2-methylpentane, 4-ethyl, 2,2-dimethylheptane. If a particular substituent appears more than one on the parent chain, then the position numbers are separated by commas, and prefixes di, tri, tetra, etc. are used to indicate the number of times it appears. Note: while deciding the alphabetical order of substituents, do not consider the prefixes di, tri, etc. 4-ethyl, 2,3-dimethyloctane. If two different alkyl groups are equidistant from the two ends of the parent chain, then the numbering is done in such a way that the group which comes first in alphabetical order gets the lower number. 4-ethyl 7-methyldecyne. Since ethyl comes before methyl in alphabetical order, therefore the parent chain is numbered from the end, which gives lower number to the ethyl group. If the group attached to the parent chain is also branched, called as the complex substituent, it is named as substituted alkyl group prefixed before the name of the parent chain. The carbon atom of the complex group are separately numbered, with the carbon atom attached to the parent chain always numbered as 1. The name of the such group is always written in brackets. When present along with other substituents, the alphabetical order is decided by taking the complete name of the complex substituent under consideration, including the prefixes di, tri of the complex substituent. 7-ethyl, 2-methyl, 5, 2-methylpropyl nonene. This is the complex substituent, and here we can see 5, 2,3-dimethylbutyl, 7-ethyl, 2-methyl decane. While naming an alkane, if two equally long chains are possible but the number of side chains attached to each possible chain are different, then the chain having larger number of side chains is selected as the parent chain. 3,5-diethyl 2,4,2,4-dimethyloctane. Methods of preparation. First, by hydrogenation of unsaturated hydrocarbons, Sabatier and Sand-Arens reaction. Alkenes and alkynes are reduced with hydrogen in the presence of a catalyst, nickel, platinum or palladium, to give alkenes. Here we can see the reactions. Use of nickel as a catalyst of hydrogenation requires a temperature of 525 to 575 Kelvin, while reaction with platinum or palladium can take place at room temperature. By reaction of alkyl halides, they may be reduced directly or indirectly. Direct reduction. Direct reduction of alkyl halides may be carried out with the following reducing agents: zinc and HCl, zinc copper couple and alcohol, hydrogen in presence of palladium, RX in presence of zinc hydrogen gives alkene, N-propyl bromide in presence of copper and zinc gives propane plus HBr. Reduction of alkyl iodides in particular may be also carried out with Hi and red phosphorus in a steel tube. Here we can see the reaction: ethyl iodide in presence of Hi and red phosphorus gives ethane plus I2. Indirect reduction. It is carried out by the first converting an alkyl halide into Grignard reagent and then composing it with water to give alkanes. Alkyl halide plus Grignard reagent. Now Mg dry ether gives Grignard reagent. Then we can do the reaction by decarboxylation of carboxylic acids. Carboxylate salts when heated with soda lime NaOH plus CO undergoes decarboxylation to form alkanes. Sodium salt of carboxylic acid plus NaOH in presence of CO gives alkane acid. Wood's reaction. Fourth one is Wood's reaction. Alkyl halides, when made to react with the metallic sodium in dry ether, give rise to alkanes having greater number of carbon atoms than the reacting alkyl halides. Rx plus 2Na plus Rx in presence of dry ether gives alkane Rr plus 2NaX. For example, methyl bromide plus 2Na plus methyl bromide here also in presence of dry ether gives ethane plus 2 NaBr. For fifth one is Coriolis synthesis. This method is a much better method than Wood's reaction for preparation of higher alkanes and consists of reactions between an alkyl halide and lithium dialkyl copper. Rx plus 2 R2CuLi lithium dialkyl copper gives alkane plus RCu plus LiX. For example, N-propyl bromide plus lithium dimethyl copper gives N-butane. Then it's Kolb's electrolytic reaction. Sodium or potassium salts of monocarboxylic acid when subjected to electrolysis gives alkanes. The reaction is known as Kolb's electrolytic reaction. 2RCONA plus 2H2O in electrolysis gives alkane. The reaction occurs as follows. Sodium salt of acid ionization gives 2RCO negative plus 2Na positive. 2H2O positive ionization 2H positive plus 2OH negative at anode. 2RCO negative plus 2 electron gives 2RCO alkane plus 2 CO2 at cathode. 2H positive plus 2 electrons gives H2. Physical properties of alkane. Physical state. Lower alkanes from C1 to C4 are colorless gases. The higher members from C5 to C17 are colorless liquids, while the still higher members beyond C17 are colorless, odorless solid at room temperature. Boiling points. The boiling points of alkanes increase regularly with the increase in the number of carbon atoms. There is an increase of 20° to 30° for each carbon added to the chain. Reason: alkanes are non-polar molecules having weak van der Waals forces of attraction between their molecules. As their molecular size increases, the surface area and hence the strength of van der Waals forces also increase. As a result, the boiling points also increase. Second one is amongst isomeric alkanes, the boiling point decreases with branching. Reason is this is due to the fact that the surface area decreases with branching and so does the van der Waals forces of attraction between them. Thus, branched isomers, which are more compact, have lower boiling point than their straight chain counterparts. For example, alkane, N-pentane, isopentane, neopentane. This one has the highest boiling point, then this, and then this. Third one is melting points. The melting points of alkane also increase with increase in molecular weight, but the increase is not so regular as seen as below. Alkane, propane, butane, pentane, hexane, heptane, octane, and their melting points are mentioned there. The increase is much more in moving from an alkane having odd number of the carbon atoms to the higher alkane than in moving from an alkane having even number of carbon atoms to the higher alkane. Reason and this is because the intermolecular forces in a crystal depends not only upon the size of molecule but also upon how well the molecules fit into the crystal lattice. Chemical properties of alkanes. Alkanes constitute an unreactive class of compounds since they all contain sigma bonds and are non-polar in nature. As such, they are inert towards common reagents under ordinary conditions. However, under strong conditions, they do undergo a few reactions, mostly substituted by a free radical mechanism. First is halogenation. The reaction involves the replacement of one or more hydrogen atoms of an alkane by corresponding number of halogen atoms. The order of reactivity of different halogens is F2 greater than Cl2 greater than Br2 greater than I2. Chlorination. Chlorination is carried out by treating an alkane with chlorine at high temperature 523 to 673 Kelvin in pressure of diffuse sunlight or UV light. It often results in successive replacement of hydrogen atoms with chlorine atoms as shown below for methane. Methane plus CH4 plus Cl2 gives CH3Cl plus HCl methyl chloride. Then CH4 plus Cl2 gives CH2Cl2 plus HCl methylene dichloride. CH2Cl2 plus Cl2 gives CHCl3 chloroform trichloromethane plus HCl. CHCl3 plus Cl2 gives CCl4 carbon tetrachloride tetrachloromethane plus HCl. The extent to which each product is formed depends on the chlorine to methane ratio. If methane is used in excess, chloromethane is obtained as the major product, but if the chlorine is used in excess, CCl4 is the major product. Mechanism of chlorination. It occurs via a free radical mechanism. Step 1 is chain initiation. It involves homolysis of Cl2 molecule to give chlorine free radicals and requires an energy of 58 kCl per mole. ClCl and it gives 2Cl free radical. This is an endothermic step and required energy is obtained from heat or light. Step 2 is chain propagation. It involves attack by chlorine free radical on a molecule of methane to give a molecule of HCl and methyl free radical. This methyl radical then collides with another chlorine molecule and abstracts a chlorine atom, giving methyl chloride molecule and a chlorine free radical. As the two propagation steps are exothermic, they are repeated several times. Methyl chloride so formed may combine further with chlorine radical to form HCl molecule and chloromethylene radical. This then reacts in further chain reaction to given dichloromethane and chlorine free radical. Similarly, by further chain reaction, trichloromethane and tetrachloromethane are also obtained. Step 3 is chain termination. The reaction is terminated by coupling of any two reactive intermediates as shown. As we can see. Yes. Now starts cycloalkanes. Introduction is saturated cyclic hydrocarbons are known as cycloalkanes. They have the general formula CnH2n and isomeric with alkanes. Nomenclature of alkanes, cycloalkanes. There are two systems of nomenclature. First, common names. They are known as polymethylenes in the common system. The number of carbon atoms in the ring are prefixed before the word methylene. For example, trimethylene, tetramethylene, pentamethylene. Second is IUPAC system. In IUPAC system, the saturated alicyclic hydrocarbons are termed as cycloalkanes. The names are derived by adding the prefix cyclo to the name of corresponding straight chain hydrocarbon having the same number of carbon atoms as the ring. For example, cyclopropane, cyclobutane, cyclopentane, cyclohexane. The cycloalkanes are often represented structurally as a regular polygon where each corner depicts a CH2 group as shown above. IUPAC naming. For monosubstituted cycloalkanes, there is no need of numbering to indicate the position of the group. For example, methyl cyclohexane, ethyl cyclohexane. For cycloalkanes containing more than one substituent, the numbering of the ring carbons is done in such a manner that the substituents get the lowest possible numbers. Also, the name of the substituents are preferred in alphabetical order along with their position. Also, the substituent which comes first in alphabetical order is given the lowest possible number provided it does not violate the lowest set of locants rule. For example, 1,3-dimethyl cyclohexane, 1-ethyl 2-methyl cyclopentane. If the rings contains equal or more number of carbon atoms than the alkyl group attached to it, then the compound is named as derivative of cycloalkane and the alkyl group is taken as substituent. For example, butyl cyclopentane to propyl cyclohexane. If the ring contains lesser number of carbon atoms than the alkyl group attached to it, or if more than one ring is attached to a single chain, then the rings are treated as substituent and the compound is named as the derivative of alkane. For example, 2-cyclopropylpentane, 1,3-dicyclohexylpropane, dicyclopropylmethane. Methods of preparation. By dehalogenation of uh, alpha and this dilates. Friends method. Treatment of alpha and this dilates dilation derivations having the halogen atoms attached to terminal carbon atoms with sodium or zinc gives cycloalkanes. 1,3-dibromopropane cyclopropane. 1,4-dibromobutene cyclobutane. This reaction may be regarded as an internal Woods reaction. Condensation dilates with malonic ester or acetoacetic ester. Perkins method. Amina dihalides when condensed with active methylene compounds like malonic ester or acetoacetic ester gives cyclic diesters, which upon hydrolysis are substituent dicarboxylation yields cycloalkanes. For example, ethylene dibromide plus malonic ester gives cyclic diester, then gives final product cyclopropane monocarboxylic acid. Photochemical cycloaddition reaction, 2 plus 2 cycloaddition reaction, also known as this. The term cycloaddition refers to an addition reaction between two unsaturated molecules to give cyclic products. Individual reactions are designated by writing the number of pi electrons of each reactant in a square bracket. During such reaction, new sigma bonds are formed at the cost of pi electrons of the reactants. 2 plus 2 cycloaddition reaction take place in the presence of light only. Example of 2 plus 2 photochemical cycloaddition is reaction between two ethene molecules to cyclobutane. Ethene gives cyclobutane. Mechanism. The reaction takes place by a converted mechanism involving cyclic transition state. Alkene, then cyclic transition state gives substituted cyclobutane. Addition of carbenes to alkenes. Carbenes add on the alkenes to give cyclopropane derivatives. This reaction is also referred to as cycloaddition. Carbenes are too reactive to be isolated, so they are generated in situ by using a suitable carbene precursor like diazomethane CH2N2 or ketene CH2 double bond C double bond O that generated carbene in the presence of light. Alkene plus diazomethane gives cyclopropane derivative. 2-butane plus ketene gives 1,2-dimethyl propane. Chemical properties of cycloalkanes. Like alkenes, cycloalkanes also contain carbon-carbon and carbon-nitrogen sigma bonds and are therefore quite inert towards chemical reagents and undergo only a few reactions. But in contrast to their higher homologies, cyclopropane and cyclobutane exhibit high chemical reactivity as they are not very stable and have a tendency to open up. They give addition reactions similar to alkenes but are much less reactive than the latter. Reaction of halogens. In the presence of light, cycloalkanes undergo free radical substitution at high temperature. Cyclopropane plus Cl2 gives cyclopropane plus HCl. Cyclohexane plus Br2 presence of sunlight gives bromocyclohexane. In presence of FeCl3 or FeBr3, the ring system breaks up to give open chain addition products. Reaction of halogen acids. Cyclopropanes addition on halogen acids to give open chain alkyl halides while the higher cycloalkanes do not react. Cyclopropanes propane plus HI gives N-propyl iodide. Cyclohexane plus HI gives no reaction. addition of water. In presence of concentrated H2SO4, cyclopropane but not other cycloalkanes adds on water to form alcohol. Cyclopropane plus H2O in presence of H2SO4 gives N-propyl alcohol. Reaction with hydrogen. When heated in the presence of nickel, cyclopropane and cyclobutane addition on hydrogen to give open chain alkane, while higher cycloalkanes do not react. Cyclopropane plus H2 in presence of Ni gives N-propane. Cyclobutane plus H2 high pressure, high temperature gives N-butane. Cyclohexane plus H2 gives no reaction. Relative stabilities of cycloalkanes, Beer-Stein theory. In the earlier days, cycloalkanes up to only 6 carbon atoms could be synthesized in laboratory and the higher rings were unknown. As far as reactivity is concerned, cyclopropane and cyclobutane were found to be much less stable than the higher members as they underwent addition reactions through ring cleavage, while cyclopentane and cyclohexane were not known to react. The difference in the reactive stabilities of different cycloalkanes was explained in terms of Beer-Stein theory, which was put forward by Adolf von Baer in 1885. Main points of this theory are: first, the carbon atoms are carbon atom constituting the rings lie in the same plane. As a result, 190 28 minutes, the bond angle between the adjacent carbon atoms of the rings no longer remains 190 28 minutes, which is a normal bond angle of tetrahedral carbon. Different rings have different values of this angle. For example, cyclopropane rings is a triangle having carbon-carbon-carbon bond angle of 60 degree only. Any deviation, position or negative from the normal tetrahedral bond angle value of 109 degree 28 minutes produces an internal strain in the ring which makes the molecule unstable. Greater the deviation from the normal angle, greater is the strain and therefore lesser is the stability. Note that the sign of deviation makes no difference. Greater the stability of ring system, the more easily it forms. Baer also calculated the angle strain involved in the formation of cycloalkanes of various ring sizes as shown in the table. Here we can see the stable angle strains in various cycloalkanes. Evidence in the Baer-Stein theory. As seen from the table above, the magnitude of strain goes on decreasing from cyclopropane to cyclopentane. Thus, the case of formation and stability should show a corresponding increase, and this has been actually found to be so. The case of formation and stability of cyclohexane can be justified in terms of the small angle strain its cause. The fact that the cycloalkane containing 7 or more carbon atoms were not known to exist at the time of Baer was attributed to the increasingly large strain involved in the formation of higher rings. This theory could also successfully account for the great reactivity of the ethylene bond. The double bond was treated as a two-membered ring in which the angle strain is 1 by 2 half this and equal to plus 44 degree 44 minutes. This large strain was held responsible for the high reactivity of double bond. Limitation of Baer-Stein theory. The theory fails to explain the following points. First, ease of the formation of the ethylenic bonds. The theory could not explain the ready formation of a double bond in spite of such a large angle involved. Second, stability of cycloalkane and higher cycloalkane. The theory failed to explain the stability of cyclohexane and higher cycloalkanes as evident from their heats of the combustion data given below. Heats of combustion per CH2 group of cycloalkane. Heat of combustion per CH2 group of the open chain alkanes is equal to 658.5 kJ per mole. Larger the heat of combustion, less stable is the compound and vice versa. From the above table, it is seen that as compared to open chain alkanes, cyclopropane and cyclobutane give 38 and 28 kilojoule more energy per CH2 group, thus indicating that they are relatively less stable, a fact which is agreement with Baer strain theory. However, on the other hand, the heat of combustion per CH2 group of cyclopentane and cyclohexane and higher cycloalkanes differ only slightly from that of open chain alkanes. This means that the higher ring alkanes are nearly as stable as open chain alkanes, a fact which goes against Bayer's theory, according to which cycloalkanes having more than 5 carbon atoms should be increasingly less stable due to the increasing deviation from the normal tetrahedral angle. So here completes our chapter. Thank you.